All right, good afternoon, everybody. Welcome back. Did anybody do anything fun over spring break? Zero fun? Did you guys at least do things for school or something? Is that what really is that? We just sat around and existed for a week straight? Tight, relatable. Sometimes that's a good way to pass your time. Cool. So I'm looking at the calendar, and our last midterm exam is going to be in not this Tuesday, not the following Tuesday, but 3 Tuesdays from now. So not tomorrow, not next week, but the week after that. That would be the 21st. Okay. I'm looking at the ways to fill up the calendar, and it's mostly just going to be examples using rotational motion stuff. There's very little to introduce before the next exam. Basically what I'm telling you for the next 2 weeks at the very least. So my vision is to do a couple of examples today. Some examples, I'll sort of tease a new thing at the end of class today. We'll do some examples on Wednesday. We'll do some more examples on, let me think about it, the following Monday. Yes, and then for the following Wednesday, that would be the 15th, tax day. Make sure you filed your taxes. And then on the 15th, we will do an exam review. And then that means the 20th, we'll start a new chapter, basically. And then the 21st will be exam 3. And then after that, I'm not going to say that you can kick your feet up and relax because we still have homework. We still have a final exam. But I will, short of guaranteeing you, I will say that there is a strong possibility that everything gets a lot easier after that. Okay. The only other thing to pass along is that next Tuesday, the 14th, we do have our last experiment of the semester. And despite its title, it's not nearly as intimidating. You're not calculating moment of inertias. You are, you're just not, using integration or anything. Fear not, it's actually a pretty straightforward lab. I think it's kind of fun. And then that's the last experiment we have. The following week is the last mandatory lab meeting we have, because that's exam 3. And then there's only a couple more weeks after that, and then we're done. I believe according to the university schedule for final exams, our final exam is going to be Monday, May 18th at 3 p.m. So it'll be in here. It says that I am legally obligated to only give you 2 hours. So my trade-off is that the exam is just going to be something that I think you can breeze through pretty fast. My hope is that it's not something where you leave feeling like your grade got worse, okay? Because I'll get to you in just a second. Unlike other exams, you don't have the opportunity to do corrections, so I don't want to, but it's also not going to be an underhand toss either. I don't want to screw you over. That's sort of the vision for what we've got left, okay? Any other questions? I know you had your hand up, or were you just...
Is it cumulative?
Say again?
Cumulative.
Oh yeah, it's cumulative. Yeah. It's all cumulative. Yeah. It's not going to be that bad. I think a lot of the ideas are going to connect together. Kind of, and sort of an example we'll do today. I think you'll see how everything fits together. Okay. Any other questions? Cool. Moral of the story is that basically today, Wednesday, and next Monday, honestly probably next Wednesday too, they're going to be shorter lectures. That's really what I'm saying. Okay. But enough of me talking. If there are no other questions, let's do a couple of examples. Oh, before I say that, my vision is I'm gonna do all the talking probably today and Wednesday. And then I think next Monday is going to be one of those days where we're going to get into groups and then I'm going to shove you guys up on the board. I think that'll be another thing. It seemed like there was mostly positive feedback for that, yes? Yeah, it was a nice idea, right? Cool. Maybe the execution wasn't perfect, but that's sort of my vision. Okay. Okay, sweet. Let's do this. My first problem that I have for today is may seem a little contrived, but my vision for today is I would like to calculate the total angular momentum. If I could separate these, geez. Note to self, get magnets that you can deal with. I'd like to calculate the total angular momentum of the planet Earth. So this is my vision of what I'm seeing here. Okay, where my green magnet is basically where the sun is. Okay, and I would like to. This is my path that the. Oh no, I don't like that. The Earth takes. Earth goes in approximately a circular orbit. Okay, something akin to that. And I'm just going to say that this is where the Earth is. Okay, we now have a new tool for adding a component of the angular momentum to a system. Okay, so whereas before, the only thing we really knew about was the orbital, the part where the Earth goes around the sun. Okay, I'm going to say that that's the direction that the Earth goes in orbit. Okay. One thing we know is that at any given time, when something's traveling in a circle, that is the speed that it's moving at. Okay, and then we know that it is moving. That is its radius. Okay. And if we have a velocity vector and a distance vector, like that, if those two things are have any perpendicular components whatsoever, then there's angular momentum. Okay, is that the only way that the Earth turns around something? What other way does the Earth turn? Yeah, the Earth itself rotates, right? That's why we have days and nights. At least that's what I learned, okay, when I went to physics school. So the other thing that not that this really matters, but the Earth rotates around a slightly tilted axis like that, okay? And this is a very small preview into Physics 4C, and I mean like really small preview. There are two versions of angular momentum that we're going to talk about, okay? So the total angular momentum, check this out. It's I'm going to say tote. And I really only care about the magnitude, actually. I really don't care. Okay, the total angular momentum is the angular momentum from the Earth going around the sun. So that I would call it the orbital angular momentum. So I'm going to call that orb. Okay. And then there's the part where the Earth is on its own. It's a spinning ball in space. So I'm just going to call that spin. Ta-da! And believe it or not, we have everything we need. Okay. I did myself the solid of looking all of this up before I got to class. Okay. Let's see. The two things that I care about. So for the orbital angular momentum, okay, the orbital angular momentum, this is going to be the part where we have to do a cross product. Not really. We sort of have to do a cross product. Okay. The orbital angular momentum, I'll just cut to the chase here. Orbital angular momentum. Okay. That's the part where we have to do r cross, and I'll put a vector sign on top, r cross the momentum that my object has in this case. Since it's traveling in a circle though, the only thing, then since it's traveling in a circle, my v vector and my r vector are always going to be perpendicular. Okay, so because I'm telling you that this is a circular orbit, it's not exactly a circular orbit, but it's a pretty good approximation, okay? Then I can jump straight to the chase and tell you that my magnitude is r times p. Okay, no sine theta is needed because they're always going to be 90 degrees to each other. Okay, this r is basically my average orbital radius. Okay, that's a value that you can look up. Okay, it's the p and it's the p part that's going to be a little bit more of a concern. Okay, this is still momentum. Nothing's changed there, so that's still going to be r times m times v. Okay, so far so good. Okay, where do I go from here? I'm assuming that this is, I'm assuming also that I'm moving at a constant speed, okay? And in fact, something that we'll do in 3 weeks, probably in short order, no, yeah, 3 to 4 weeks, we'll talk about is that when gravity is the only thing that's keeping you around, then angular momentum is always conserved, okay? And that since I'm traveling in a circle, that means my speed is going to be constant. Okay, as soon as I bend it and I make it an ellipse, that's when things get weird, okay? That means the speed that I'm traveling is the distance that I cover divided by the amount of time it takes. So what would be the distance that I cover in this case? What's the name for the perimeter of a circle?
Circumference.
Bingo. It's my circumference, okay? So my velocity is some distance that I travel over time. So that's going to be r, and that's m. My distance that I cover is 2 pi times my average orbital radius. And then the time that it takes me to do that, is, I'm just going to say my orbital period. How long does it take for the Earth to go around the sun? 365 days, exactly, okay? So this is just 1 year, okay? So I've got everything I need now. My orbital radius is, there's 2 r's here, so I'm gonna say 2 pi times the mass of the Earth times r squared divided by t. Now the goal, we're gonna get that into seconds, but we've done this before. It's not tremendously complicated, but it's still work we have to do nonetheless. That's it. Okay, we're gonna plug in all our numbers at the end though, so hang tight. Okay, that's part 1. Okay, part 2 is one that's gonna freak us out a little bit. I'm gonna change colors, but only a little bit, okay? The spin part, okay, let's see. There's basically like a wedge that's going through the middle of the Earth, okay? The spin angular momentum part is gonna be a little bit different. Okay, this is basically, what shape is the Earth approximately? Sphere. Would you say the Earth is mostly hollow, or is it mostly solid? I'd say it's probably mostly solid, right? Okay, it's not like there's not like, I don't know. I'm not going to speculate. Okay, it's mostly solid. Okay, and it's rotating around the center, I would say. Okay, so instead of an MV and an R, okay, where this is a point, now we have to talk about a 3-dimensional object that's spinning. So what do you think? What's a quantity that you think is going to be involved here? Yes, gravity's mostly over here. So instead of MV and R, this is really what I was going for. The angular momentum is going to be the moment of inertia. I know you're going to freak out. We already did it, so we're not going to redo it. Don't worry. That's the thing that I was going for. That's the component we're going to talk about. Okay, but we already know what that is. We went through all the trouble right before we went on spring break, no less. we went through all the trouble of finding what the moment of inertia of a solid sphere is. Okay, we figured out what that is. Okay. We'll talk about what the angular velocity is in just a second, but we also know what that is. Okay. We're assuming that the planets that we're talking about is a solid sphere. Okay, we did this. I'm going to use little m because that's the, and then I'm going to call the radius of the Earth capital R. Okay, that's different from the orbital radius, but nonetheless, we need some radius in there somehow. Okay, and then what about this omega part? Okay, the angular velocity. Okay, how long does it take the Earth to spin around itself? That's 24 hours. It's a day. It's a definition of a day. So the angular velocity, but we're talking about how long does it? Okay, so the angular velocity. Okay. And then how many radians do you cover in a day if you make one full rotation? 2 pi. Right on. So it would be 2 pi divided by, I should have used a different one. I'm going to use little t. Okay. This is the period of spin, which is 1 day. Ta-da! And just like that, you have everything you need again. All right. I'm going to put all of those pieces together. Okay, so I've got, let's see, I've got a 2/5 mr squared, and then I've got a 2 pi. So that's going to be, at the end of the day, that's going to be 4 pi times the mass of the Earth times capital R squared. I think that's everything on top. And then it's all divided by t. And that's just 1 day. Oh, thank you. Thank you. There is a 5. The 5 goes on the bottom. Cool. Thank you. Good catch. I will just, for the sake of full disclosure, I didn't think about physics one bit over spring break. Cool. That's everything we need. I know the mass of the Earth. I know the average orbital radius. Hopefully we all know how long it takes for the Earth to go around the sun. I still know the mass of the Earth. I know basically the average radius of the Earth too. And I know how long it takes to go around, okay? You can do all the math yourself, but basically, at the end of the day, the total angular momentum is equal to, I'm gonna write everything out, so that'd be 2 pi times m times little r squared, which is different from capital R, and then that's plus 4 pi m capital R squared divided by 5 times t. My goal is to get all of those in the same units, so kilograms, meters, seconds, okay? The number that you get at the end of the day, when I did this, was something like 2.7 times 10 to the 40th kilograms meters squared per second squared, something like that. That's 40. That's a really important thing. Okay. The biggest contribution, without a doubt, is the orbital angular momentum. It's several orders of magnitude bigger than the spin angular momentum. They're both huge though. Sweet.
Did you factor anything out when you were doing the math for that?
You could factor out an m and a pi and a 2. Yeah, I don't know. I did not though. Yeah. It doesn't. They mean the same thing. Sweet. If you're ever bored, you can add all of those things together for all the planets. I would put all of that in a spreadsheet though. So look up all the data for all the planets, and then you can add them all together. You can even include the sun. The sun just doesn't have an orbital period. It stays more or less fixed in place. Cool. I don't know, if you're bored, think about it. Any questions on that one? Yeah.
How you said the orbital one is like much greater, that's because of the sun's gravity is just so great, or what's the reason? Why the orbital
Coincidence?
is greater than the rotational?
I'd probably just say that the orbital component's just bigger, just because the I guess the imaginary lever arm is bigger, so it's sweeping out a bigger distance. I don't know. As to why, cosmic coincidence as far as I'm concerned. Yeah. Anything else? Sweet. I feel like aside from teasing all of that information out, that's actually it's not the worst thing ever, right? Not the worst thing you've ever seen in your life. Okay? You can also disagree with me. You can say, Mr. S, that is absolutely the worst thing I've ever seen in my life. But given some of the calculations we've done recently, I'm inclined to think that this is a nice little break. Cool. Okay, the next one is not a nice little break. If there are no other questions, then we'll move on to the next example. Okay. In physics, I think you'll notice a pattern. It might just be me, but physicists love doing things on inclined planes, on inclined slopes. So it's time that we, ooh, that marker was sticky. It's time that we do something that involves rotations. Where we let something roll down a hill. Okay. So I'm going to let something roll down a hill. The thing I'm going to let roll down a hill, so this is a classic question that I'm sure you guys know the answer to, but I'd like to get a precise answer. Okay. Let's see, that is some angle theta. This is I'm going to let another ball. That's my ball. Okay. My ball has mass m and radius r. Okay. And it's going to roll. This is only going to play a roll at the end, some height h, down the hill. My question is, I have two questions. So number one, when I let this go, how long does it take to reach the bottom? That's going to be the harder one. And then number two, how fast is it going when it gets to the bottom? Okay, two questions. So part A would be, what's the time when I release it from rest? How long does it take to reach the bottom? So the time it takes to go from here down here. Okay, and then my question, part B, is how fast is it going? Equals question mark. Okay, buckle up because we've got some work to do here. Okay, an important caveat here is that the ball in question is going to roll without slipping. Okay. So an important take-home point here is if a ball, so I'm going to say ball rolls without slipping. Okay, that means by definition, okay, the linear speed at any given time, okay, is the same as the oh my god, why am I so lost for words? It's the same as the angular momentum times the radius, okay? So by definition, as soon as you see something rolls without slipping, your first order of business here is that V is equal to omega times the radius of my ball, or whatever's rotating, by definition. First thing you should think. Okay, so where do I go from here? If I'm completely lost, okay. Do you guys remember the advice that I gave you a long time ago when I said as soon as you see time involved, what is the topic of physics that is almost certainly involved? Better question. Okay. What's up? Yes, acceleration is involved. I guess a better way of saying that. Did we ever really see time when we talked about energy conservation? Not that I can remember. We never really saw time involved with energy conservation, okay? So energy conservation is out of the equation. Did we really ever talk about time when we talked about forces? Not really, no. Okay, what was the one place we explicitly saw time? Kinematics. Bingo, okay. So if I'm asking for time, kinematics is somehow involved. Okay, so keep that in mind. My end goal here is going to somehow involve kinematics. Okay. But we've got a lot of work to do before we get there. And admittedly, this is one of the harder problems that we're going to talk about. Okay. So for part A, I know kinematics is somehow going to be involved. Okay. And at least one place I would like to go is maybe I can figure out how far down this goes. Okay, I can figure out the length. Okay, maybe I'll call this distance. Maybe I'll call that distance. I don't know. We'll call it D. I don't know what I'm going to call it. I'm going to call it something. Okay. If I know how long the distance that it travels over, and an important caveat that I didn't mention is that this is released from rest. Okay. One thing that I know is that D is going to equal 1/2 a t squared. Okay, that's one place I can start. Okay. The one thing I'm told, the two things that I'm explicitly told though, are h and theta. So I'll have some way of getting from my letter D if I know h and theta. Okay. So maybe that'll be helpful. I'm not sure. Okay. So my big goal here is going to be to figure out what A is. Okay. And then once I know A, the T is going to be really almost directly going to fall out. So the thing that I know immediately is that, let's see, T is going to be the square root of 2 times the distance it travels divided by whatever acceleration I get. Okay? Whatever acceleration I get, it's whatever acceleration I get. Okay, so this is the thing that I need to figure out. Okay, and believe it or not, we've actually done something similar to this. Not identical, but similar. Okay, one place I can start. This is a. Maybe have we had a teacher in our lives to this point who you look back and you say, man, I think they've changed my life like forever. Have we had a teacher like that? Never had a teacher like that? Okay. New life goal. Okay. I had my calculus teacher in high school. Probably flipped my world upside down. Changed my life forever. One of the things that she used to say was that if you're ever lost, literally just start writing things down, and then write down everything you know, and write down every single relationship you could possibly think of. And then once you run out of ideas, that's probably the time when you can start connecting things together. Okay, so in my world, okay, this is how I would do this. I am, okay, my secret sauce is almost always, to make your life easier, my secret sauce is always to make my y direction perpendicular to the surface that my ball starts on. So I'm going to call that y. That's y. And then that's x. Okay, there we go. Okay, and then I'm going to do the same thing I almost always do. Okay, that's still mg. Nothing's changed there. Okay, but okay, I still have x and y components. And my ball, that's still the normal force, okay? Relative to the horizontal or the inclined surface, my ball isn't moving up and down. It does, in other words, it doesn't move this way. It doesn't move into the incline and it doesn't move out of, okay? Okay, so the first place I'm gonna start is with Newton's second law, and you might think that's out of place, and you're not entirely wrong. So I'm going to say that the sum of all forces, and I know what you might be thinking is that, Mr. S, you said that this was rotational motion. I know. Sum of all the forces in the y direction, that's going to be my normal force, and then that's minus mg, but that, hopefully this is something that's familiar to us. Okay, this is mg cosine theta. Okay, and since it's not moving up or down in this direction, in the diagonal direction, like that, if it's not moving up or down in that case, what's my acceleration? Is, with my water bottle right now, okay, is it moving at all? Not in our shared reference frame, right? Okay, so what's the net acceleration on my water bottle right now? It'd be 0. Yeah, same deal. In the diagonally perpendicular direction, sweet. Okay. Okay, yeah.
Could be a dumb question. Cosine theta, it looks like to me that it's the hypotenuse. Is it mass and gravity is on?
So yeah, mg would be the hypotenuse, yeah.
And so how do we get the cosine?
Okay, this angle here and then this angle are the same angle. So in the vertical, in the y direction, this would be the adjacent leg of the triangle. That's where the cosine comes from.
You're saying the normal force would be the adjacent?
The y component is this component. The y component of gravity, that would be mg cosine theta. And then this component that goes that way, that's mg sine theta. In other words, you see what I'm saying? Cool. I know, it's Newton's second law from several weeks ago coming back to bite us. Does that help? Okay, cool. Sweet deal. Okay, the thing that this tells us is hopefully nothing new, is that my normal force is just mg cosine theta. Okay, the next part is the x direction. Okay, this is where things are moving. Sum of all the forces in the x direction. Okay. That would be, okay, now if something is rolling without slipping, what do you think is the thing that's causing it to turn? There's something that's pushing on the ball that's going to make it turn. what's making it turn? Say again?
The inclined angle.
I like where your head's at. Yes, that's not wrong. Okay, right now. Okay, so a better question. Okay, if I clamped my fingers on the side of this, okay, am I going, when I push this along the table, do I experience some force that's opposing me when I push it along the table? Exactly. Okay, so when I let this go, what's the thing that's going to make it rotate? Yeah. I get bonus points for catching it. Okay. Okay, so keep that in the back of your head. Okay. This isn't, if there were no friction, then this would just slide down. Okay. Otherwise, then we wouldn't really have we wouldn't have a super exciting fun problem to do. Okay. So there is friction opposing us, and I'm going to use my fancy F to do that. Okay. So the thing that's going down the hill, that's going to be mg sine theta, okay, and then that's just minus F. Okay. And I'm going to leave it, I'm going to sort of leave it right here. This is going to equal, what did I say? I'm going to change that. That's little m. That's little m now. Okay. And that is m a. Okay. Okay. So that's one of the things I'm looking for. Okay. But because we're in rotational motion land now, now we have to worry about the rotational contribution of the ball. Okay. So the last step in this case is I've summed up all my forces. The last thing I want to do is sum up all my torques now. Okay. So the last part is sum up my torques. Okay. Okay. The question is, okay, if I let a block roll down the hill, or slide down a hill, right? In the past, we've said that that's accelerating. Okay. Now that this is turning, okay, what did we agree is going to make this thing turn? It's friction. Okay. So the friction, okay, maybe I shouldn't have colored that in. Okay. I'm gonna do this over here. That is a terrible ball. Okay. But that is my radius. Okay. And which way is friction acting? It's the force itself is acting parallel to the surface, right? But against the direction of motion. Okay. So friction, that's the direction that friction is acting. Okay. If it's acting only at the point of contact of the sphere and the inclined plane, wouldn't you say that despite my crappy ability to draw realistic images, wouldn't you say that that's perpendicular, the force and the radius of the ball? That's pretty slick. Okay. So if I'm summing up all the torques acting on my ball, the sum of all my torques, that's going to be friction. Okay, to be precise, it's R cross F. Okay. In this case, the force in question is friction. Okay, and then it's times the distance away that it is going to be the radius of my ball. So it's F times R. Okay, and since it's 90 degrees, I'm going to drop the sine theta because it just turns out to be 1. Okay, did that justification make sense to everybody? Did that track? Cool. Okay, yeah, that's the only thing that's making this thing turn. Okay, gravity is making this thing go down, and friction is the thing that's making this turn. Okay, so in the same way that once I've summed up all of my forces, I tack on an MA at the end. The thing that I do at the end of summing up all my torques is I do an I times alpha. I sum those things up. Okay. So I know it's easy to get lost in all this is the extent to which I'm going to write a bunch of stuff out. Okay. The only other thing I can think of is, okay, my goal was to figure out what A was. Okay, that was my goal. There is a way for me to get from alpha to A. Okay, in the same way that I can use omega and the radius of my ball to get between linear velocity and angular velocity, I can do the same thing in this case with A is equal to alpha times R. Okay. So here's what I'm going to do. Okay. Since I know everything I need to know about alpha, I'm just going to solve for alpha in this case. It's going to be F. Oh, actually, you know what? No, I lied. I'm going to solve for friction. Okay. It doesn't matter, but this is how I did this. I'm going to say that friction is I times alpha divided by R. That way I have something that I can take directly over here. Okay. We're headed in the right direction. Okay. The only other thing that I'm going to throw in here is that alpha is equal to my linear acceleration divided by R. Wait, no. Yes, okay. So I'm going to substitute that in here. So that's I times A, and then now I have two R's on the bottom, so that's an R squared. Okay, we're actually almost done. Okay, I'm going to substitute what I figured out for friction into my x direction. So I get, let's see, I get m, I'm going to substitute this, I'm going to put that in there. So I get mg sine theta, and that's going to be minus I times A divided by capital R squared. Okay, and all of that equals m A. Okay, my goal in the very beginning was to figure out what is A. I have everything I need. Okay, so I'm gonna blah 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 blah. I'm gonna cut to the chase here because I don't want to. You guys can do all of the rest of the steps on your own time, but I get A is equal to let's see, that would be G, there's a factor, oh, I'll just leave the, so it's mg sine theta divided by m plus, let's see, that would be I over R squared. Okay. I figured out what my A is. Okay. The only other thing I need to know now is for whatever object's rolling down the hill, okay, I better know what the moment of inertia is, okay? I'm going to start by saying that this is a solid ball rolling down a hill, okay? So the last thing I need is what's my moment of inertia, okay? And then I'll know everything I need to put this back in here. Okay, so the last thing I need was I for a solid sphere. Okay, that was 2/5 m times capital R squared. Okay, and then that's going to go right in here. So let's see what I get. Okay. Or this is, I get, okay, yeah, never mind. I'm not going to make any comments yet. So I get mg sine theta, and that's divided by m plus, let's see, that'd be 2, I'm getting ahead of myself. I'm way too caffeinated. 2/5 m capital R squared, and then that's divided by R squared. Oh, thank God. I was hoping that I would get units of acceleration at the end. Okay, so I get the R squared, and the R squared cancel out. And then I have a factor of m on the bottom and on the top. So at the end of the day, let's see what I get here. So 2/5 plus 1, that'd be 7/5. Okay, and then that's on the bottom. So at the end of the day, I get, well, let's see, 7/5. So that would be 5g times sine theta divided by 7. That is my acceleration, okay, for the case of a solid sphere. Okay, if I told you that this was a hollow sphere, I don't know, like maybe if this were on an exam or something, what would be the one thing that changes to this point? Yeah, the I that we use, okay? So in the case of a hollow sphere, okay, we figured out that was 2/3, okay? Okay, and just as a point of comparison, that would be, let's see, that would be 2/3 on the bottom, so that'd be 2/3 plus 1, that'd be 5/3? Let me think about that. 3/3 plus 2, yeah, that's 5/3. So this would be, the A for a hollow sphere would be 3/5 g sine theta. Okay. Okay, so a couple concept checks here. Okay. Number one, if I replace this with a box, okay, do you think in all likelihood that a box is going to go spinning downhill? Could, right, if it were steep enough, but in the past when we've done these examples, have we had boxes rolling down hills? Probably not, right? We've had boxes sliding down hills, okay? So if my box, if it were just sliding down a hill and there was 0 rotation, okay, so in some universe where I could pin this ball in place, what's the one part of my acceleration equation that just goes away? If there's no rotation. I don't have to worry, okay, I don't have to worry about my moment of inertia, do I? If I don't care where my mass is, if it's not spinning, I don't care about it, right? So if that goes away, okay, if my moment of inertia is gone, then it's just an m on the bottom, and then it's just A is just g sine theta, which is exactly what we figured out in the past, okay? Okay. The one difference being that that's the one time then we would have to worry about the friction contribution here, and we'd have to know what that's about. Okay. Let me think. Okay. Okay, I figured out what the acceleration is. Okay, that I can put everything together in here, and now let's see, for t, I can delete my crappy drawing over here. Okay, t, let's see, that's 2d, that's square root of 2 times d, and then I'll say this is for t solid, okay? That would be, let's see, that would be 5g sine theta divided by 7 on the bottom over here, okay? And then square root that, okay? I'm gonna clean that up, okay? The thing that I know, and we'll get back to this in just a second, okay, the thing that I know is h and theta. The last thing that I'm going to do is I'm going to say d is equal to, or actually better way of saying this is h is equal to d sine theta. So I have a way of saying that d, let me think here. Yeah, d is equal to h divided by sine theta. Okay. Okay. I don't think that really added anything to my world here, but let's see here. So that would be square root of 2 times h. Oh, and then there's a 7 on the bottom, So that's going to go up to the top. That's going to make that 14 divided by 5g sine squared theta. And all of that's in a square root. Okay, man, that was the ugliest thing I think I've ever seen in my life. That is the least attractive formula we've ever seen so far. Okay, so quick concept check. Okay, if if I have flat ground, okay, what does my angle become if it's flat ground? Sorry. If this is flat ground, I'm taking my incline and I'm squishing it down here. So what does my angle become in that case?
0.
It's 0, right? Okay. What's sine of 0 in this case? Oh, sorry, yeah. What's sine of 0 degrees?
0.
It's 0, okay. So as a concept check, okay, so I get sine of 0, I have a 0 on the bottom, okay, that effectively, as to a physicist, that means that if I have a 0 on the bottom, what doesn't matter what's on the top, what happens? If I have a 0 in the denominator, what happens? We get an explosion, right? It blows up, okay? That effectively means that as the angle gets shallower and shallower, that it gets more. That means more and more time. And when it's flat ground, okay, when I get truly flat ground, how long do you think it's going to take my marker to roll across a flat hill? It's infinite amount of time. That's what I'm saying. That's where I was going with that. So I've got some good concept checks here. Okay, the only difference for the hollow sphere was just the acceleration. So same deal. I still get 2d, and then it's divided by 3/5 g sine theta, and then that turned into 10d. That turned into 10h over, let's see, yeah, 10d over 3, and that's g sine squared theta in a square root. Sweet. Okay, so if I fix h in place, let's say that it's just 1 meter, and I say that my angle is 30 degrees, just for a point of comparison. Which one's gonna take longer here? Okay, which one's gonna take longer to get to the bottom? A hollow sphere or a solid sphere? Same mass and same radius. Say again? That one's gonna take longer? Let's find out. So just as a point of comparison, okay, here's a better way of saying this. So in both of these, I have an h and a g and a sine squared theta. So my question to you is, which one's bigger, 10/3 or 14/5? Okay, that's my question to you. So is square root of 14 over 5, is that greater than, less than, or are they equal to square root of 10 over 3? Okay, I don't know. Let's see. To me, 3 times 3 is 9. So that's almost a little over 3. Let's see what I get. 14 divided by 3. Oh, sorry, 10 divided by 3, I'm dumb. 10 divided by 3. I get something on the order of 1.82. So this is 1.8, I'll say 1.83 and call it off there. Square root of 14 divided by 5 I get something on the order of 1.67. And those are seconds. Okay, so moral of the story is that, generally speaking, a solid sphere is probably going to move faster. Solid sphere is going to be easier to maneuver in this case. It's going to accelerate faster, okay, or it has a lower moment of inertia, which means it's easier to accelerate. It takes less energy. Okay, so I don't know. For those of us who plan on doing mechanical engineering stuff in the future, you don't have to walk through this entire calculation again. But if you're given the choice between materials, okay, let's say that you're using ball bearings, or God forbid, if you want to use a bunch of ball bearings to roll something down a hill, the thing that's going to make that thing move down the fastest is probably going to be a solid sphere, right? If you wanted to, let's say, roll something down slower, or if you wanted to slow it down, you might consider doing something either bigger, or you might consider doing something that's hollow and having more mass concentrated on the outside. Practical application here. Dang. All of that was part one. Okay, believe it or not, part two is going to be a lot easier. What's the speed? There's two ways you could do this, by the way. There's two ways to do this. Okay. Part two is what's the speed when it reaches the bottom. Okay. This is almost the exact same thing as, let's say, I'm dropping a ball and I don't care how fast it's rolling. I want to know how fast it's moving when it hits the ground. The only thing now that we have to keep in mind for the rolling down a hill part is now I have a rotational component. Okay. So for part B, what do I want to erase? I'm going to erase this part. So okay. So for part B, there's two ways to do it, but in my opinion, energy conservation is almost always going to be the easier part. Okay. Okay. So the total mechanical energy initial is the same thing as the total mechanical energy at the end. Okay. If my ball starts at rest, what is my initial kinetic energy? Total kinetic energy, for that matter. 0. Okay, so this is going to be potential energy initial. Okay, and then if I have reached the bottom, what is my height at the bottom? 0, yeah. And so I'm imagining that I'm going to be moving faster at the end. So that's going to be, I'm going to say kinetic energy tot final. Okay. The difference is, so not only do we have translational speed, the last thing we have to consider is the rotational speed too. Believe it or not, those two things all add together. And I'm just going to do the solid sphere one. Okay. So I start at MGH. Okay, nothing changed there. Okay, the problem now is I have 1/2 mv final squared. Okay, but now I'm spinning too. So I have 1/2 I omega squared. This is the secret step for most rotational stuff, or with things that are rolling. Okay, I know a couple things. Okay, I know I know that for the solid sphere, I'm just going to say solid, is 2/5 m capital R squared. Okay, and number 2, I know that omega is equal to v, my linear speed divided by r. So those are the two things that I know. So I'm going to plug all of that into my second expression here. And just as a reminder, this is translational kinetic energy. That's when things move through space. Okay, and then this was the rotational kinetic energy. That's KE. Rotational, that's when things are spinning. It's a different kind of motion. Okay, so I get, check this out, 1/2 mv final squared. And then I guess that would also be final. That would be 1/2 times, okay, hang on for the ride here. We get 2/5 mr squared times, okay, the omega squared is v final over r quantity squared. So check this out. I have an r squared on the bottom over here. I have an r squared on the top, okay? So those cancel out. And then I have a 2 that cancels on top and bottom. So what I end up getting here is 1/2 mv final squared plus 1, let's see, that's 1/5 mv final squared. The secret step for all rolling motion is just making, and when you're asked for what the speed of the ball is at the bottom, is to always remember that your way of getting back and forth between rotation land, with rolling motion anyway, is that the linear speed is the same amount that the ball rolls. The ball spins. And let's see, so that would be 7/10. 7/10 mv final squared. So if I want to know what my final speed is, then I just got to solve for it. And wouldn't you know it, oh, just by the way, those two things are the same. And just like all things gravity, mass just doesn't seem to matter, no matter how hard I try. So the final speed at the bottom is just square root of g, let's see, that would be 10 gh divided by 7 square root. Okay. So the biggest difference between ball rolling downhill versus, let's say, block sliding down frictionless plane is just the rotational part for energy conservation purposes. Those are the only two differences. Okay. I believe I answered both my questions. What's the speed at the bottom, and how much time does it take? Okay. Are there any questions on these two examples that we did today? A lot of moving parts, a lot of things to consider. Okay, and this is why rotational motion is hard for a lot of students, is because even though I thought I got rid of Newton's second law, it still comes back to bite you. Okay, and it turns out that we kind of needed it. And even though I thought I was done with kinematics, we still came back and we needed it too. Okay. Any questions on anything? Nothing? Cool. We'll come back on Wednesday and I'll briefly introduce a quasi-new concept, something that we've more or less seen before, but now we have a new way of talking about it. We'll do at least one example. Maybe we'll get our hands dirty a little bit and actually do some stuff. But I think other than that, folks, that's all we've got for today. I will see you back here at the very least on Wednesday afternoon.